Okay, here we go with a question. This is HL looking at the structure of the atom. Okay, as ever, have a go, and then when you're ready to see an attempted explanation of the answer, please press play. Okay, so we've got the Geiger, Marsden, Rutherford experiment. Pretty sure it used to be called the Rutherford experiment when I was at school, but they've obviously changed that, so no worries there. And we are firing alpha particles, and they've been accelerated, and they're instant on gold. We know the proton number, and we want to know the distance of closest approach. I think it's a really nice question because it's a good understanding of your application of energy conservation. So let's talk about that. I start from this point of view, which is that the total energy is conserved. Now, I appreciate there's a lot going on here. There's going to be loads of equations on the slides. My apologies if it gets a bit confusing. I don't really know how else to do this, so let me know if there's anything that's unclear. So we've got energy conservation. The way I've put it here is the change of potential energy, kinetic energy plus the change in potential is equal to 0. That means the total energy change is equal to 0. Therefore, if we know our change in kinetic energy, we know our change in potential energy, and that's what we're looking at here. The change in the kinetic energy is a little bit confusing here, so let's go through it. We've got to remember that we first accelerate our alpha particles, and they then decelerate. So this change in kinetic energy is referring to the second part of that, which is where the alpha particles are decelerating. Now, to calculate the change in kinetic energy, we're going to think what we had at the beginning and what we had at the end. At the end, it's fairly simple because at the distance of closest approach, we have 0 kinetic energy. At the beginning, we had the energy which was due to the work done by the potential difference or the electric field. So we're using here -2, so we're doing 2 times E times the number of volts, which is 7.7 MV. So I've written that there as 15.4 MeV. Okay. The reason I've done that is because this question here has got things stated in symbols, and I think that's going to be important later. Why is it a minus sign? Well, we had kinetic energy, we've lost kinetic energy, and so therefore we've lost this much kinetic energy in the process of moving to stopping. So if we followed that, we can then hopefully see that if we take our change in kinetic energy and add it to the change in potential energy, we're going to get 0. The change in the potential is a little bit different. We're going to use KQQ over R. And again, the bit that's changing there is the R. We've got 1 over R2, take away 1 over R1. That's the change in 1 over R. And we've got this multiple at the front, K times Q times Q. And again, I've kept it as 2 times E, 79 times E. Why a 2? I probably should have mentioned that early. It's because we've got an alpha particle with a charge of +2. We're then going to hopefully simplify this. We're going to say that R1's infinity. Remember, at the beginning of this experiment, we assumed that we've gone very far away from the nucleus, and therefore we're at an infinite distance. And that's going to simplify our little equation. We're also going to set R2 equal to X. That's the final distance. That's our distance of closest approach. We're going to put those numbers in, noticing that 1 over R1 is going to disappear. 1 over R1 is going to be 1 over infinity, is 0. We've got 15.4 MeV plus K, 2E, 79E. I've not done any multiplication there. I'm probably being a bit unclear there. There we go. Finally done the multiplication. We've got an E squared coming from the 2E times 79E and the 158. And all we're going to do is just going to work through the maths and end up with our final equation there. We're going to bring the sign on there, absolutely. We're going to rearrange for X, and we are going to have K times 158 E squared over MeV. Now, this is where we have to think about the type of answer we're looking for. We're looking for an expression, and we're noticing here, for example, we've got an E squared over an E, so we're going to cancel one of those E's, and we're going to look at one of these answers here, but the question is which one's which? Well, we know that M is times 10 to the 6, and after doing a little bit of maths, this 158 divided by the 15.4 comes back to a 79 on the top and a 7.7 on the bottom. That's just taking a factor of 2 out, which means our answer here is C. Now, I appreciate there's quite a lot going on here. There's quite a lot of maths. It's a pretty tricky way. I'm sure there's another way of doing it. This is the way my brain works. If you've got any questions, please let me know, and I'll try and answer them in the comments.